Monday still online session. So Monday, because Wednesday you need to come to the classroom. So we swap the original in-person meeting on Monday, we swap it to Wednesday, in-person test. So officially, our Monday session is the next week is also online class. So that's the, yeah. So in that way, so I do not need to make any special announcement. Yeah, just let you know. Yeah, but I will post the announcement message before Monday. Reminder message before Monday. All right. What else? Yeah. If you have any questions, just let me know. Oh yeah, no display. Oh yeah. So I forgot. All right. Yeah. Now it's good. All right. All right. Yeah. There is one slide about coding part, yeah, but I feel it's not that important, so I skipped that slide. You know, the technical consideration in coding of Quicksort. So that part, I do not worry. It is pretty easy. All right. Worst case efficiency of Quicksort. Yeah. When we do analysis like this, we need to review our previous understanding. Because think about, when we do divide and conquer, how do we split the data? We split the data in two subarrays, and we choose the pivot element. But when we choose the pivot element, it's a random selection, right? Yeah. The pivot element is selected in a random way. Then your device step may not give you a balanced data distribution. Sometimes more balanced, sometimes more unbalanced data split. So that kind of behavior would cause a worst case. If your data split is extremely unbalanced, yeah, extreme cases, extremely unbalanced, then we will get a worst case. Yeah. So let's look at the situation. Now, the worst case happens when the partition is extremely unbalanced. That means your pivot element is near one of the two endpoints. There are two endpoints, left end and the right end. If your pivot element is very close to one of the two endpoints, then that's the extremely unbalanced data split. Yeah. All right. For example, this case. Your pivot element, its location is at the end of the array. Yeah. So all the remaining data belongs to the first subarray. That's the first extreme case. Yeah. So you only have one S region. You don't have the L region. Yeah. Another extreme case. You only have L region. You do not have S region. Yeah. So these are the two extreme cases. Extremely unbalanced data split. Yeah. And sometimes you may change from these two extreme cases here, there, sometimes the first extreme case, sometimes the second extreme case. And when that happens, you will get the worst case efficiency. So let's look at, in the worst case situation, how many comparisons do we need? Yeah. It's very easy to get the answer. Yeah. You can see in these two extreme cases, every time when you complete one partitioning step, you need to use n-1 comparisons. After n-1 comparisons, you only reduce the problem size by 1. This pivot part, the pivot element is in place. That's the only part you can reduce the problem size. That's too small. The size reduction is too little in that situation. Yeah. All right. So then you can see if you always, so let's imagine our worst case. If in all of our partition steps, we always get one of the two extreme cases, then at the end, we will get the worst case. All right. Yeah. But here we look at the comparisons. Yeah. So we do not look at the swap. Yeah. Because comparison operation is the basic operation. Yeah. Swap operation, sometimes we have more swaps, sometimes we have fewer swaps. Yeah. Slightly different. Yeah. All right. Recurrence relation for the worst case. To calculate the number of total comparisons for the worst case. So let's look at the recurrence relation for the worst case. Yeah. So we use capital T function represent the number of comparisons for data size n. All right. After we use n-1 comparisons, we can only reduce the problem size by 1. So we have this recurrence relation. Then you do iterations again and again. Then at the end, what do you have? You add up consecutive integers from 1 through n-1, you get this many comparisons. That is in big theta of n squared. Yeah. Very bad. That's our bottleneck case, right? Bottleneck. Yeah. Very bad. Yeah. Now, let's recall. So far, we have learned 5 sorts, right? Yeah. Starting from selection sort, bubble sort, insertion sort, and the merge sort. Now, number 5, quicksort, the 5th one. You can see among these 5 sorts, only merge sort, the worst case, is much better than other sorts. Yeah. So that's one of the main properties of the merge sort. Yeah. So let's recall. Merge sort. Worst case. efficiency. It's in big theta of n log n. N log n. That means we eliminate the bottleneck case. Yeah, this n squared is the big bottleneck. Yeah. So the merge sort avoids this bottleneck situation, but Quicksort does not. Quicksort, the overall efficiency is much faster than the merge sort. Overall efficiency. How do you know it? We cannot see it from efficiency analysis. Because they both, so Quicksort, merge sort for average. So here let's look at the average. Average case efficiency. Quick and merge both n log n. Both n log n. They are in the same category. So from our rough analysis, because our analysis usually very rough, we cannot see which one faster, which one slower. But when people do experiments, you just run these two sorts on the same set of data, and you do experiments many times. Many times. Yeah. Yeah. Small number of times, so you may not get good results. So you need to do plenty of number of experiments. Then you can see Quicksort is clearly faster than merge sort. Yeah. All right. Another thing, when this worst case occurs for the Quicksort, so we know, the data that gives us two extreme unbalanced cases. But here we want to see the inputs. What kind of inputs gives us this worst case situation? Data inputs. So you can see two types of inputs. Yeah. Data ordered data. You can see ascending order. The data is already ordered. When the data is already ordered, then your partition, one of the two extreme cases. Another is descending order. The data is in descending order. You get a extremely unbalanced data partition. So these two typical cases, definitely you may find other worst cases. Other worst cases you may find. Because these two cases we can mix, right? Part of it ascending order, part of it descending order. How about that? Right? So think about, So definitely you have more different inputs that will cause worst case situation. Yeah. All right. But this ordered case, ordered case that corresponds to the worst case that may be against our intuition, because data is already ordered. So we do not need to do any sorting work, right? We do not need to do any sorting work. The data is already ordered. Yeah. But when you apply the quicksort, you get the worst case. Yeah. Another, our experience. Yeah. Recall the insertion sort. Insertion sort. Yeah. When the data is ordered, for the insertion sort, we get the best case. We get the best case efficiency. That's big theta of n. The fastest possible. That makes sense, right? Because data is already ordered. There is no inversion, right? Remember, there is no inversion. If there is no inversion, by our natural understanding, we feel the sorts should run the fastest case, right? Yeah. Should be in its fastest case by our natural understanding. No inversion. So that probably, yeah, I remember I gave you a similar question in the midterm, right? Part A. Part A, quiz number 3. Oh, regarding the quiz, after today's class, probably sometime tomorrow, I need to assign you quiz number 4. Yeah. Quiz number 4 covering module 4. We need to do one quiz. Yeah. Yeah. Sometime tomorrow, so you will see it. Yeah. All right. So the midterm part A, quiz number 3, yeah, I remember I gave you a similar question. Yeah. The input array has no inverse. We pick an arbitrary comparison sort. Do we always have the best case efficiency, right? Yeah, you know, idea like that. So if the answer is no, yeah, not because you do not have to know, because when you do the midterm, you have not learned this quicksort, right? This quicksort is a counterexample. This quicksort is counterexample. When the data is ordered, you get the worst case, not just best case, the worst case. Yeah. But when you answer that question, even without the quicksort, you can use selection sort, bubble sort, even in ascending order, right? Even ascending order. So you do not do faster than unordered case. Yeah. So when you use other sorts, many other sorts, even if the data is ordered, only the insertion sort, yeah, I would say the most likely, when you do insertion sort, you can do much faster. But other sorts, you may not do faster. Yeah. All right. So now with this quicksort, you can understand much better. Yeah. All right. Then next, yeah. So here I show you some concrete worst case. You know, partition by partition. Yeah. Every time you only reduce the problem size just by 1. Yeah. Yeah. So at the end, yeah, you get the worst case. Yeah. All right. But next, let us look at the best case efficiency for the quicksort. Yeah. from the data split point of view, for the best case, we should split our data in the most balanced way. We happen to get our data split always right in the middle, just like the merge sort. It happened to be that, although the probability is very small. That's our best case. All right. Study the best case. All right. So the two subarrays have almost the same data sizes. The corresponding recurrence relation, like this. T of n, number of comparisons for the whole array, but after the split, the data sizes become approximately n over 2, 1/2 of the size. And we need to conquer two such subarrays, not one, so two. The partition step, we need to do this many comparisons. All right. That's the best case. To estimate how many comparisons we need for the best case, here we use a approximation way, because it's very hard to do very accurate analysis, because this part is hard to work technically. N over 2, sometimes integers, sometimes non-integers. Very hard to control. So here, let us use a rough way, approximate way. All right. And this big theta, we need to use some constant, because we cannot use asymptotic notation in our calculation. So we will use constant multiple times n to replace this big theta term. Then, to estimate the cost, we need to construct a recursion tree. I mentioned this recursion tree in merge sort. At that time I said, because in the Quicksort we will do it again, so I skip that one. So we only need to talk about it once to save some time. Now let us look at the recursion tree. How do we apply the recursion tree method to estimate capital T function? The idea is very simple. Recursion tree. All right. When we start, first let's estimate the number of levels in our recursion trees. How many partitions do we need when we run Quicksort? So this inequality gives us approximate number of partitions, this k. Every time we split the data right in the middle, so we have that k. So k very close to, so here I try to do some more accurate analysis. So why this? Because n over 2 to the k plus 1, if this corresponds to the data size. Data size. After, so here, so for any positive integer n, we can find two adjacent power of 2. These are two adjacent power of 2, such that this n falls between these two power of 2 numbers. So then we do the transform of this inequality. All right. Yeah. Yeah. Now let's look at our recursion tree. Yeah. But here we know k approximately equals to log base 2 of n. Floor function, ceiling function, but very close. Here we do rough estimate. So we don't worry about +1, -1. Yeah. Good enough. Yeah. So we use this approximation for k. All right. Then in this recursion tree, we only store the non-recursion term. So this part recursion term, yeah, because t function, we need to keep doing the recursive function call. We keep doing the recursive function call. Yeah. So that part, we do not calculate the cost directly. So each node, we only store the non-recursion term. Because that part stays there, that non-recursion, we need to pay, right? Yeah. After that partition, we need to pay this much cost. Yeah. So we store what we have paid for that number of comparisons. Then we need to accumulate all the cost in all levels. The top level, the total cost is C multiple of M. Second level, there are 2 nodes, but if you add up the total cost, you also get a C multiple of N, right? Then the third level, you have 4 nodes. Each node, yeah, because the data size becomes 1/4. So each node, you have 1/4 of the C constant multiple of N number of comparisons. But when you add up subtotal of the cost in this level, you also get Cn. Then we look at the total number of levels. Total number of levels, k, right? Yeah, k levels. Yeah. So you may have k plus 1. Yeah. If you want to count the exact, if you count the exact number of levels, that is k plus 1. Why? Because the top level, it corresponds to power of 2, 2 to the 0, right? Yeah. 2 to the 0. Second level, 2 to the first, and so on. So the last level, 2 to the k. Then you count the superscripts from 0 counting through k, that is k plus 1. But that 1 is not important. So we just take k part. Yeah, k. Yeah. All right. Yeah. So k in this range. Then our estimate. We have k levels. Each level, the cost is Cn. So k times Cn. That is in big theta of n log n. So for the best case efficiency, the quicksort is in this n log n category. Yeah. So that's the way we use the recursion tree. Yeah. Yeah. It's good enough. Yeah. So we can see. Yeah. But the best case is not like insertion sort. Insertion sort, now you can see insertion sort its best case is really, really good. Big theta of m, very special. For other sorts, it's very hard to get this good best case for other sorts. So now, from this example, you can see the special property of insertion sort. When the data is almost ordered, so this insertion, this property of the insertion sort, why it is the best. Right. Yeah. All right. So that's the analysis. Yeah. Average case, I mentioned, average case, just do experiments. Yeah. All right. Then the last part, improve the performance. So there are some simple ideas people can use to improve the efficiency. Here I mentioned a little bit to give you better overall picture about understanding of the quicksort. All right. How to improve? Improve, when we talk about improvement for the quicksort, we want to avoid the worst case situation. So the basic idea, if you can find a way to avoid the worst case situation, then you can improve the overall efficiency. But there is a question. How much work do you want to do to improve your data from the worst case situation? That's one big question we need to look at. All right. The first method is randomization technique. Randomization technique. Yeah, right? From the name, you can guess the meaning. Its specific meaning is because we have one step, we select pivot element, right? Yeah. We select pivot element. How do we select pivot element? Then there is some special consideration here. Yeah. So let me talk about this randomization technique. If we do not use randomization, first let's look at the original quicksort without using randomization technique. We just use the last element as the pivot element directly. Yeah, because it is good enough, right? Yeah. From the probability point of view, we always select the last one or first one. Probability is the same. Yeah. But why something could be wrong, right? Because now we need to look at, because when the data is ordered or descending order, ascending order or descending order, these two cases, if you still use the last element or first element 100%, you will get the worst case, right? Yeah. That's really bad. Yeah. 100%. Yeah. And we know ordered or descending ordered data could occur, right? That could occur. So we want to break it. Break the pattern. How to break the pattern? by randomization. So we do not use the last element or the first element as the pivot. We run a random function to select a random element in the given array and do one swap. Swap that randomly selected element to the pivot location. The last one or the first one. So we do just one swap before we run our partition step. That's called the randomization technique. Yeah. But before any partition, you need to do one swap operation. Okay? Yeah. So random sampling. Yeah. So there is a small amount of added cost because one swap, you need to do some work, right? Yeah. So that's you need to pay a little bit in order to break the pattern. You need to pay something. Yeah. All right. Yeah. So that method, very simple. You do not need to do too much work. Yeah. But you can improve. You can avoid those extreme cases. Yeah. In some extent. Yeah. All right? Yeah. So that's the first technique. Second technique called the median of three method partition. Median of three partition. Yeah. So the idea is also very simple. So this idea, we select three elements, not just one. Yeah. We select arbitrary three elements. Yeah. Because the idea still, we want to avoid the extreme or unbalanced data distribution situation. But how do you avoid? This time, people want to do a little better than this randomization method. Slightly better. Yeah. So we select three arbitrary elements, and then we find the median of three. You need three comparisons for the worst case, right? Yeah. Yeah. Sometimes best case, sometimes worst case. Yeah. The average case, a little better than the worst case. Yeah. 2 something, 2 plus, less than 3. Greater than 2, less than 3. Average case. Yeah. All right. So then you find the median. You use that median of 3 as the pivot element. Yeah. But you need to do a little more work than randomization technique, right? Yeah. Because you need 2 point something comparisons on average. Worst case, you need 3 comparisons to select your pivot element. You need to do more work. Yeah. Can you get a better partition on your data? Probably. Yeah. But how much better? It's unknown. It's hard to know. Yeah. All right. So these 2 special techniques people can use to improve the bias a little bit. Yeah. All right. But then there is another question before I talk about this, the result, experiment result. There is one question people can ask. All right. How about, so we select, for each partition, we select the median of the array as the pivot. Yeah. So it is a bad idea, very bad. This idea is very bad. Yeah. Why? Because how do you find the median? Do you want to find the median? the number comparison you use 5 median, you know, that cost is too high. That cost is too high, much higher than your partition step. Your partition step, you do much less work than finding the median. So you only one step. You want to find a perfect pivot, yeah, because median is a perfect pivot, right? But the cost is too high, too much higher. Several times of the whole partition step. So definitely it is a really bad idea. So we cannot do that. Too costly. All right. So that's so nobody wants to do that. All right. Then now I make some final comments about the final result. Doing experiments, because these two ideas, we need to write a program to do testing on random data. Yeah. I did that before. Yeah. I assigned project to my students before, long time ago. Yeah. But the result, here, I just tell you the result. The result, these two improvement ideas, the overall result, efficiency results for these two techniques, slightly worse than the original Quicksort. Slightly worse, not better. Slightly worse. Why? Because the data, yeah, because we use the randomly generated array, the array by random function. The randomly generated function rarely ordered or ascending order, descending order. It's rare. Random generated, very random. For that kind of data, the partition, we have always not a very unbalanced, near balanced, close to, the distribution part, not very bad. Somewhere in the middle, not too bad, not too good, somewhere in the middle. In that situation, these two techniques do not help. These two techniques do not help much, but you pay, right? Because when you do the swap here, median of 3, you paid something. You slow down the algorithm a little bit here, but the gain is less than the cost you pay. The gain is smaller than that. So the overall efficiency, so these two slightly worse than the original case, original Quicksort. So that's our experiment results. So you can get an idea. Yeah. All right. All right. Yeah. So let me finish the. So this is the design idea, but our experiment results different from this. This is the, people feel these two techniques may help improve. In the general case, but so based on this experience, so if you have no reason to do this, because if you know your data has some significant percentage in ordered case or descending ordered case, then you have reason to apply this data. If you do not have any information on that, then you just use the original Quicksort. It should be faster. If no information, you just apply the original Quicksort better than, these two techniques. Yeah. All right, so we finish part D. Next, let's move to module 5. Our last sort, our sort number 6, Heapsort. Another special type of sort. But this one, the idea also very interesting. The idea related to data structure design. Because so far, of all 5 sorts we have learned, we do not use fancy data structures. We just use ordinary array as our data structure. But we want to look at a special example. We need to do some special work in the data structure part in order to make our sort have some special properties. Let me jump to module 5, part A. All right. Yeah. Slow. Yeah. All right. Heapsort. Yeah, let me do introduction. Before our break time, let me do a short introduction. Yeah. So after the break, so let's look at the main idea. Let's look at the data structure part. Yeah, yeah. I notice your side is very slow because, yeah, I can see the screen sharing. My 2 other computers, but you still see my color change part, right? But I complete that step, 10 something seconds ago. Yeah, so that's quite slow. Yeah. Now let me look at when I run my PowerPoint slide if it is too slow. Otherwise, so your understanding will fall behind about 10 something seconds. Yeah. Oh, yeah. Yeah, let me see. I changed the slide, but yeah, you just see it. Let me push my remote control button another time and see how long you need to see the change. All right. So I just say push. Oh, good. It's pretty fast. Yeah. Otherwise, it's hard to explain anything. All right. For this special sort, we need to think about why people need another sort, right? So you need to give some reason. Because so far we have learned 5 different sorts. The first 2 sorts are useless. Selection sort, bubble sort, too slow. No good properties. The first 2, mainly for education purpose. No application values in the real world situation. But the last 3 have some application values. Insertion sort, merge sort, and Quicksort. Yeah. All right. So now the question, why we need to learn another special sort, Heapsort. So in the real world situation, when people need to develop a new sort, usually there must be special business requirements on the data part. Special requirements. So here, let me give you these special requirements. For some business reason, If you ask why people need this kind of requirements based on their business, in order to avoid something, specific business problems, they need data with these properties. The first special requirement, worst case efficiency must be in this category, big theta of n log n. That makes sense. Avoid the bottleneck, right? Yeah. Because if you do not make this requirement, sometimes your sort may have bottleneck. Yeah. If some business applications do not like the bottleneck to happen, then this first requirement is needed. All right. You can see merge sort could be a candidate, right? Merge sort. But there are other requirements. Then the merge sort is not qualified because there are other sorts. The second requirement, in place. Oh, here, did I give you the concept in place algorithm? Yeah, here, I need to. Yeah, so I may not give you. Probably if I give you, I just recall this concept. It's called in place algorithm, not elements, because in place, for this terminology, there are two meanings. Yeah. This is the algorithm meaning. Yeah. For element, in-place elements, we know its meaning, simple meaning. But some algorithm, we call them in-place algorithms. That meaning is the extra space, remember? Extra space used. We know the meaning, extra space, right? Space other than input, output. The extra space used must be in big theta of 1. Then it is in place. So other than the efficiency part, there is also some requirement on the space usage. We know I give you the primary computing resource, secondary computing resource. The space usage, that's the secondary computing resource. So that part, for some special business applications, people need the extra space used must be in big theta of 1. So that's the in-place algorithm. So that's the second business requirement. Yeah. That makes sense. Yeah. Because if you do not control extra space used, then when the data becomes larger and larger, you may run out of memory resource, because all your data you need to load into the main memory. You may use too much storage space. That could happen. Yeah. So this second, with this second requirement, the merge sort is not qualified. Merge sort is not in place. Merge sort. Remember, when we do the merge step, we need a destination array, right? When we merge two arrays or subarrays, we need to copy our data to a destination array. The size of the destination array, not in big theta of 1. Big theta of k. That's too much. That's too much. Okay, all right. Yeah. So this second requirement. Third one, maintain dynamic data efficiently. So that's another special requirement. Dynamic data. So We know dynamic data. So what's that? Your data comes in and go and leave. So you maintain dynamic data. That's quite common in many business applications. Quite common. So you do not just run your sorts on fixed array. Not on fixed array. So your data, so when you run your business applications, you need to add new data items, or you need to remove old data items. That's the dynamic data. So when you do operations on dynamic data, you want to make it efficient, make your operation very efficient. So this is the third special requirement. Okay? Yeah. So our current sorts cannot support this requirement. Requirement number 3. All our current sorts do not support. Because there is no built-in special structure to support this requirement. Our current 5 sorts all work on ordinary arrays, right? Ordinary arrays. When you store dynamic data in ordinary arrays, think about after one new data item is added, you need to do a lot of work for the insertion, right? When you do deletion, you also need to do quite some work. So for that reason, a new sort must be designed to have all these 3 properties. All right. Yeah. Yeah. So later I will explain these things again. So when we get to the design part, data structure design part, we need to go through the data structure design. Yeah. So we will look at it again. Yeah. Insertion, mainly about insertion. Yeah. Deletion, more complicated. Yeah. Insertion, you also need to come to insertion. Because deletion, you leave some location empty, right? Yeah. But you want to reorganize your data structure. So then, a lot of work you need to do. Yeah. All right. Yeah. So regarding the insertion, when you do insertion operation, what do we mean? We have efficient insertion operation, right? So if here, people have this kind of understanding. For people with some experience, so when they talk about efficient insertion operation, if you need a big theta of n number of comparisons to complete your insertion operation, then it's not efficient. Because this corresponds to the linear insertion. It's a linear insertion, linear efficiency. So that is very slow. All right. People want to have this binary insertion. Yeah. Because log base 2 of n, that's the binary type insertion. Then it's acceptable. Yeah. People can call it, this kind of insertion is efficient. If linear insertion, not efficient. If it is binary insertion, people can call it efficient. So we target binary insertion. All right, yeah. idea. So we need to make it happen. Here you have some ideas, but we need to make it happen. Need a new data structure. We need to select an appropriate data structure. All right. This data structure, because here there is a binary insertion operation we need to do, so we may like this data structure support binary insertion. So a binary tree structure is needed in this data structure. All right. Design. But we do not want to create a very complicated data structure. So we want to make our data structure as simple as possible. We want to avoid the complexity, but still we can do the jobs required. All right. The candidates here. Let's look at our candidates for the data structure to represent a binary tree structure. One, we still use array as a candidate. At this point, we do not know how to use an array to store a binary tree in a simple way. We don't know at this point. But at least there is a chance, right? So as a candidate, we can consider array as a candidate. Another one, linked list. Then it makes sense because to represent a binary tree structure, you need to represent the branches, right? Left branch node, the right branch node. Then linked list, you can point to the left subtree and the right subtree. So that's a candidate. Another candidate we can think about. Array, much simpler than linked list. Right? When we work on arrays, we feel very comfortable. We are very familiar with arrays. But for linked lists, when we work on linked lists, we need to do a lot of special operations, a lot of work. All right. So if array can do the required work, then we like to choose array because of its simplicity. If array cannot, do these things, then we have to choose next candidate, linked list. So our first priority, we want to see if an array can store a binary tree or not. If we can use simple array to store a binary tree structure, then we do not need to go to the linked list. So let's try our best to make it happen in an array. All right. So then maintain dynamic. So here I talk about binary, linear. So just repeat that process. So let me, efficiency. Here, let me quickly complete that. Because build a binary tree structure in an array. So here, I talk about that, binary insertion. Yeah. The data not in order, the new data comes in not in order, so we want to insert it, make it in order. So for the insertion, there are two ways. A linear way, we reject it. Because based on people's understanding, people feel the linear insertion too slow. So this idea should be rejected. So the target is the binary insertion. That's acceptable. People are satisfied with the binary type efficiency. All right. So now for the insertion. Next question, how to make it happen? So we know our goal. So in our mind, we know what we want to get. But how? We don't have any idea how to make it. So the next step, we need some smart idea to build a binary tree inside an ordinary array. Array, so simple, easy to work, but how can you make a simple array to store a binary tree? That's the technical question we want to solve. When you store a binary tree inside an array, remember, you need to do operations on that binary tree, right? You need to traverse the binary tree from the root node to other nodes along the edges of your binary tree. Those things you need to consider. All right? Yeah. Next, we need to consider a new data structure. All right. And we want to make an array as the underlying data holder. All right. But to make it support a binary tree, the most important technical problem we want to solve is we want to maintain the parent-child relationship. How do you traverse your binary tree inside an array? You need to use the parent-child relationship. How do you describe parent-child relationship inside an array? That technical problem we need to solve. We need to find a simple solution on this technical problem. All right. Yeah. Binary tree structure in array. Yeah. So that's the one important step. All right. How to build binary tree inside an array? Define parent-child relationship. Okay, all right. Introduce the heap data structure. Now, we need to talk about a special heap data structure. What is a heap data structure? Okay, yeah. Before we solve our technical problem, so we need to study some background knowledge, heap data structure. properties we need for this heap data structure. So use an array as underlying storage object. Heap. So this heap. All right. This heap is a near complete binary tree. What is a heap? Yeah. Near complete. So the question is, what do you mean near complete binary tree? Right? Yeah. All right. Let me stop at this point. So we take a break. Then at 7 o'clock, when we start our second half, then let's look at the whole data structure design based on this heap data structure.